Welcome to our discussion on the law of cosines. As always, feel free to fast forward to the section you want to look at. I have a feeling a lot of you will be fast forwarding through this first section where we look at how we can derive the actual law of cosines. On the surface, I agree, these three formulas look quite scary and daunting, but if you really look closely at them, you'll see they're very simple. A, B, and C are just the lengths of the three sides of the triangle. Simple, just numbers, right? So we've got A, B, and C in different permutations down here. Nothing too scary, just squaring some numbers. 2 times a combination of two of those numbers, again, pretty easy. And then just taking cosine of an angle. Very, very simple. Okay? So don't let the length of the formula fool you. It's still very easy to work with. Now, how does it differ from sine or the law of sines? Well, you remember the law of sines were ratios where we had sine of an angle over its side was equal to sine of another angle over its, sorry, that should be a B, over its side, etc. Do the same thing with the angle inside C. So when do you know when to use one or the other? Well, if you'll recall, we could only use the law of sines if we had one complete pair, right? We had to have an angle and its side, and then we had to have one of the other two, and then we could solve for the missing piece, right? We've got 4 variables here and one equation. We can only solve for one variable in one equation, so we need 3 of these pieces. So you need an angle and its side and another side, or an angle, its side, and another angle. Okay? Now looking down here, we can solve for missing pieces as long as we have the other two. These are all pretty much the same formula. They've just been solved for a different letter. You can see that if we're trying to find A, we really need to know B and C, right? Because they're also both here. And then we need to know the angle that goes with A. If we want to solve for B, we need to know the other two sides, because again they go there, and then we need to know the angle that goes with it. So there is some overlap here, right? If we're trying to, let's say, solve for B, we would need to know the other two pieces, so we would need to know A, and we would also need to know C. And then if we're trying to solve for B, we also have to have its angle, which means we have to have this piece, right? So if we have this, I'll put them in red, the things that we have. If we have B, we have A, and we have C, we don't have enough to solve for what we need, right? The B with the black arrow, because we would still need this other angle A. And if we had that other angle A, then I would use law of sine, because that's a lot easier. So the big difference here is we really need 2 sides and an angle, and we're good to go. Up here, we can still get away with 2 sides and an angle, but they have to be the right 2 sides, right? And here, not so much. So that's the big difference between the two. Okay, let's look at how we try to derive this. Here are 2 generic pictures for trying to derive this formula. We could either have an acute triangle on the left, right? Angle A is acute, or an obtuse triangle on the right where angle A is obtuse. Angle A is being centered at the origin, and so we're measuring its angle as normal. And you can see that these 2 cases now take into account all angles except for right angles, right? A right angle is neither acute nor obtuse. It's right in between at 90. But with these 2 groups, we have all triangles. Let's just look at the left one. Okay, so remind yourself that this point C is on a unit circle, and I'll try and draw our circle-ish thing, right? Well, it's not necessarily a unit circle, right? It's centered at the origin and it has a radius of b. So we know that if we do, and we'll just call this angle A. Okay? If we do cosine of angle A, well, cosine, remember, is the ratio of this distance divided by that distance. So it's going to be x over b. So if we wanted to solve for x, or if we want to figure out what this distance was, we just multiply both sides by b. So we get b cosine of a equals x. And that's what they have right there. And then we can do it over again and look at how sine of a, right, is opposite over hypotenuse, y over b, and so y equals b sine a, and there's our y piece. Okay, so if we have a triangle with an angle centered at the origin, like this, then we know this point C is always described by the hypotenuse times cosine of A and the hypotenuse times sine of A. Okay, that's the first step. We also need to recognize that this point here, B, is just some distance C from the origin, right? This, if you put the triangle up here where you can see it without the axes, this distance is A, this distance is B, and this distance is C. So ergo, this point right here, right, that's B, remember, because the angle is always opposite the side, so this is angle A, and this is angle C. We know that this point here, the point B, is a distance of C from the origin, so there's its coordinates, C comma 0. If we wanted to find this distance A, we could just use the distance formula. Very simply, if you remember what the distance formula is, right? A is just the distance. Let's do small d, distance, because we don't want to get confused with maybe an angle d, if there was one. The distance between C and B. So A squared is just going to be this distance squared. Now, what is that distance? Well, I mean, what's the distance formula? If you remember at all what that distance formula is. Well, you might remember that the distance formula is basically the square root of the change in y's squared plus the change in x's squared. But since we're trying to find a squared, if you square both sides, you get rid of that square root. So you have a squared equals, well, our change in our x's, right, from this point to this point is b cosine a minus c, right? That's the distance going from this point to there. It's basically this distance right there, squared, plus now our change in y, so we're going from this height down, this distance here, and that's just b sine a minus 0, right, because that's a height of 0, and then we square it. Okay, FOIL everything out. A squared is going to be b squared cosine squared of a minus 2bc cosine a plus c squared. When you square this, since you're minusing 0, you're just squaring this piece. So you just get plus b squared sine squared a. Now you'll notice that you have a b squared piece here and a b squared piece here. So we can combine those. B squared times cosine squared a plus sine squared a minus 2bc cosine a plus c squared. And now what is cosine squared plus sine squared? Doesn't matter what the angle is, right? Cosine squared plus sine squared just equals 1. So that goes away. And you're left with simply b squared plus c squared, I just moved this one in front, minus 2bc cosine a. That's equal to your a squared. And there is the first version of the formula. We could derive the other two by just taking the triangle and rotating it and putting point B at the origin and doing it all over again, and then putting point C at the origin and doing it all over again, and you get the other two versions of the formula. So really all that's going on here is we're using the distance formula and the identity of cosine squared plus sine squared equals 1, and that's where the law of cosines comes from. So we can find the length of a side based on the lengths of the other two sides and then a cosine piece, right? So now we know the length of this side, a, technically a squared, but still it's giving us its length in terms of everything else, right? We can define that by the b and the c and then the angle. So all we need to know is this distance, and this angle. So if we have side, angle, side, we can get everything else. So we use the law of cosines whenever we have sine, angle, side, SAS. Which brings us to our next thing, is when to use it when we have SAS, sine, angle, side. Here's our first example. We want to solve or figure out triangle ABC where we have A is 15, there's our side, B is 10 inches, there's our side, and then C, there's our angle of 60. And you think, well, how come that's not side-side angle? Well, if you drew a picture of a triangle, right, it doesn't matter what it looks like, just some generic triangle, A, B, C. They tell us this is 15. They tell us this is 10. Where does angle C have to go? It has to go here, right? The angle is always opposite the other side, right? The side that it's named with. And so now we have side, angle, side, and we have a SAS triangle. So all we have to do is use the law of cosines formula. Very simple. We use the one that is solved for C. Plug in everything we know. Slap cosine of 60 into our calculator, or if you have it memorized, you know that it's just 1/2. The right hand side simplifies to 175, so C has to be the square root of that, or roughly 13.2, and we just found the third side, right? The length of the third side of the triangle. Could we find the angles, right? Would we be able to find the other angles now at this point? Yes, because now we could use the law of sines, because we know that sine of C over C has to be sine of A over A. So we have sine of 60 over C, which we just found, 13.2, is going to be, and where would A be? Remember, A would be this one here. It's going to be sine of A over A, which is 15. And it's also going to be sine of B, this one, over its side 10. And we can now solve for the other two angles. So you can always use a combination of the two to get all the bits and pieces of the triangle that you need, which is what we're doing here. Finding the other angles. Angle B, and then of course angle C we can just get from knowing they have to add up to 180 degrees. And there is our nice little table with all of our measurements. You'll notice that the ones that we found all have the squiggly equals because those are approximately equal. Okay, how about another example that's more of an applied example? So we have some plane flying over a point headed due south at 550 miles per hour. 20 minutes later, another plane passes over that same point with a bearing of 37 degrees east of north, right? It's going north 37 degrees east at a speed of 1250 miles per hour. And they want you to find the distance between the two planes 3 hours after the second plane passed over that one point. And they want you to round your answers to the nearest tenth. All right, what's the first thing we should always do with a word problem? That's right, draw a picture. There's our point. We're always going to let the point that we're dealing with be the origin. It just makes the most sense, and it makes our life easiest if we center things on the origin. So that D there stands for Disney World, right? That's the point that they're traveling over. The first plane is heading due south. That's this one, heading due south. The second plane, the F-16, is north. Right? Remember, it was north and then 37 degrees east. So if you go 37 degrees east from due north, that's where you get this angle and that trajectory. Right? That's the bearing that the F-16 is flying. Now, if we start the clock when the second plane travels over Disney, when the F-16 passes over it, then the time for the Boeing is plus 1/3, because remember the Boeing passed over 20 minutes before, so it's already gone 1/3 of an hour. We're letting T be hours. So now this distance is growing at a rate of 552 miles per hour times the time that has elapsed. That's why we have to do it in terms of hours, because the rate is in miles per hour. So the plane was going at 552 miles per hour. When we start the stopwatch, when t equals 0, it's already traveled this distance because it had a 20-minute head start, right? A 1/3 of an hour head start. And then as the other plane starts going, its distance is modeled by its speed times the number of hours, 1250 times t. Okay, so now we have these two lengths written in terms of time, because they're not static, right? They're moving as the planes, they're growing as the planes are moving. We're trying to find this distance d. So we're just trying to solve for that distance right there, d. If we use the law of cosines, we know that d squared is a squared plus b squared minus 2ab AB cosine of the angle that is associated with d, right? These formulas, it's always the angle associated with the side, and the angle associated with this side is the 143. If this is a 37-degree angle, we know the leftover bit from 180 gives us that 143 degrees right there. Plug all that into the formula, substituting in t equals 3 because they wanted you to find out how far these two planes were 3 hours after the F-16 had passed over Disney World. And you get a d squared of this big old number. When you square root it, you get d of roughly 5,300 miles. Okay? Simple stuff, right? Don't make this any more complicated than it is. Yes, it's an ugly looking formula. Yes, it can be scary, but it's really very simple to use because all you're doing is plugging in numbers, squaring some things, adding them. It's all basic math operations. So don't overthink it. Draw yourself a picture, figure out what you have, figure out what you need, plug in the stuff that you know, solve for the one you don't. Very easy. Okay, that's for SAS. What if we're trying to solve for SSS, right? Side. So how about we're given the triangle ABC where they just give us the three sides. If you draw a picture, we have, here's angle A, angle B, angle C. So that means that this side over here is B, 5.4. This one over here is A, 3.1. And this one over here is C, 7.2. Now you could really pick any of the three laws of cosines here because you have all three sides. And whichever one you choose is just going to be the angle you end up solving for. So we picked C. We know this, we know this, we know this, we know this, we know this. One thing left, easy to solve for, right? And in fact, algebraically, that's what they're doing here. They're solving for cosine of C. They're getting it all by itself. They subtract the a squared, they subtract the b squared over here. So they got c squared minus a squared minus b squared. And then they divided by this. They divided by negative 2ab. And what they did here is they multiplied top and bottom by a negative 1 to kind of cancel these negatives, which is why this becomes negative, positive, positive, and positive, and that's how they got that piece. So now it's just simply, gosh, plug in A, B, and C. Couldn't get any easier. Square some things, right? Plug all that in your calculator, and you get negative 0.39. So now we know that cosine of this angle C is equal to negative 0.39. So how do we solve for C? That's right, we just take the inverse cosine of that. So C is just going to be the inverse cosine of that amount that we had, which comes out to be roughly 113 degrees. Now you got to do is rinse and repeat, right? Do it 2 more times. Well, actually, you'll have to do it 1 more time to find another angle, or you could just use the law of sines, right? Now that we have an angle and its other side, right? Its side that's created by that angle, you can always go back to using the law of sines to solve for other missing pieces. Get the second angle there at 43.7, and then use the rule that they have to add up to 180, get the final angle, and you're done. There's your side. Very simple stuff, guys. Don't overthink it. Okay, how about another final example where we're solving an SSS triangle. You can see that everything's still the same. 2 meters, 9 meters, 5 meters. So we have our 2 meters, 5 meters, 9 meters. This was A, so this has to be A, right? 5 was C, so this has to be C. And then 9 was my B, so that's got to be my B. Again, we're just going to use the formula to solve for one of them. This time we decided to do it for B. Plug in everything that we know, right? Solve for it like we did before. Plug in everything, and we get cosine of B equals negative 2.6. And what's wrong with that is we know that the cosine function only has answers between -1 and 1. Its range is from -1 to 1. So there is no angle B that would solve this, and therefore this triangle cannot exist, which makes sense because look at my picture. The distance between A and C is 9. And we all know the shortest distance between 2 points is a straight line. So there's no way that we could travel along this side and it would be less than 9. Yet in this direction is 5, in this direction is 2, 5 plus 2 is 7. That's impossible. That triangle does not exist. Okay, last part of this is using Heron's formula to find the area of a triangle. Just like before when we were dealing with the law of sines and we had a special angle formula for a special type of triangle, we have Heron's or Aaron's, depending on how you want to pronounce it, formula for a side-side-side triangles. We can find the area of the triangle with the three sides A, B, and C using this simple formula. Again, it might look complicated because it's long, but if you really look close at it, you go, well, that's pretty simple. It's just A, B, and C, which are just the lengths of the side, and then there's this S thing in there, and this S thing is called the semi-perimeter, and it's just simply 1/2 of the sum of A, B, and C, right? That's what a semi-perimeter. Perimeter is all the way around something, so A plus B plus C is the total perimeter of your triangle, and the semi-perimeter is just half of that. Couldn't be any easier. Obviously, you don't want to try and write that thing in as S, because then that formula gets really ugly. Instead, just take it as a two-step process. Figure out what S is, and then plug that into the formula for K. As we will do here. Here is our triangle, 29, 25, 40. You should always check and make sure that it actually is a triangle. 40, 29, 25. Where's the longest side? Here's my longest side, 40. So the distance between these 2 points better be, and I could have these letters wrong, sorry, because A is 29, B is 20. Oh, look at that, I did it right. And then just by guessing. And then C is 40. The distance between A and B is 40, and that has to be the shortest distance. So the sum of these two has to be greater than that. And in fact, that has to be true for any two sums. These two have to be bigger than 25, and then these two have to be bigger than 29. But since 40 is the biggest number, we know that those two by default will always work. For instance, if we look back at our other example where it was 9, 5, and 2, 9 plus 5 is bigger than 2 because 9 is the biggest, right? 9 plus 2 is bigger than 5, again because 9 is the biggest. So really all you have to do is check the side where 9 is the biggest and then add the other two. This one fails, not a triangle. These two bigger than 40, it's a triangle. It works. Okay, now that you know that it's a triangle, you can go ahead and find S by plugging in the three sides, dividing by 2. Very simply, there's your 47. Then take that and the sides, plug it into the formula, and bam, there's your answer. About 361 square inches. Very simple. Another example that's more of a word problem. Side lengths, how many gallons of water will fill the pool to a depth of 15 feet? Round your answer. So somebody decided to build a very strange triangular pool. Right, and then something like that. Right? Looks like a big wedge of cheese as far as the shape of your pool. And so if we know the area of this surface, then all we have to do is multiply it by the height, and that will give us volume. And they told us that this thing is, we'll say 17, 23, and 26. 26 is the longest one. Check. Yep, those work. So this is a triangle. It's good to go. It's the height, right? The depth is 5. So we can find the volume by finding the area of this triangle and multiplying it by 5. First things first, find S, 33, simple. Next, plug it in to find K. There's the square feet, right? So that's the surface area. Like if we had to create a pool cover, we would need that many square feet of material to make the pool cover. And then multiply that by 5 gives us that third dimension, gives us volume, and it's 961 cubic feet. Now that we have cubic feet, the last thing we have to do is convert that into gallons. We know that 1 cubic foot contains approximately 7.5 gallons of water, so we multiply our answer by 7.5, and we get a little over 7,200 gallons of water to fill the pool. And that's it, guys. That's just the last kind of application problem for this lesson. Again, don't get confused or scared by these formulas. They're very simple. You're just plugging in some numbers, you're squaring them, you're taking a cosine of an angle. Very, very simple. The hardest part is if you just come across a question and it asks you to find various things. How do you know when to do law of cosines versus how do you know when to do law of sines? Well, you always want to do law of sines first because it probably feels easier. So it all depends on what they give you, right? What kind of information do you have? Do you have side, 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 or side, angle, side? Those are law of cosine triangles. When you have the other combinations, angle, side, angle, 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 those types of things, then you use law of sines. Okay, it's that simple, guys.